All right, let me switch over to presentation. And we'll get started. So good evening, everyone. I'm going to turn off my video. I'm going to ask that you do, actually I'll leave mine on, but I'll ask you to turn yours off to minimize bandwidth. And you can certainly turn your video back on at some point when we get to the end of the program here, and we can all chat afterwards. So we'll do it then. So if you don't know me, my name is Mark Minerich. I am your president of the astronomy section of the Rochester Academy of Science. Welcome to the December virtual meeting. I want to thank Dave Pesch and his company Expudo for letting us use this service. It's been a real boon for us. We've been using this since April monthly, and then we've done some start parties with it. We've also had board meetings using this service, so it's been a pretty tremendous service for us to be able to use this. I want to make sure that we thank Dave and his company for letting us use this. It's really been a godsend. All right, so how this works, if it gets noisy, you get a lot of background noise, I'll probably mute you. Please don't be offended. If you want to speak, you can always unmute yourself. If you go straight down to the bottom of the presentation, you'll see a microphone. If it has a slash through it, you're muted. If you click on it, you'll be able to speak again. Regardless of who mutes you, you can always unmute yourself. So feel free to unmute yourself if I happen to mute you. There's chat available. You may see that there's some chat in there right now. You can chat to the whole group, or you can chat to somebody directly. Feel free to do that, whatever. When Kelly starts to speak, if it's a question you'd like to ask, I would ask that you chat it, and I'll interrupt Kelly to answer the question, or at the end you can also ask questions that way. If you're going to be talking during these things, I recommend using a headset because it does take out a lot of the background noise that happens around you. If you have a headset on, and you don't get any background echoing that happens as well. All right, so here's our agenda tonight. I'll do a welcome. We have some announcements. And then our featured talk tonight is by Kelly Douglas, who's a professor of physics and astronomy at the University of Rochester. And her talk title is Mapping the Universe with DESI, which is about to come online very shortly. All right, so first I want to welcome the Mohawk Valley Astronomical Society. Looks like there's a few members here tonight, so welcome, guys. Glad to have you here. And we'll hope to maybe share some of our resources over our virtual lives here for a while. So welcome. Thanks for coming. Is there anybody here, this is their first meeting, outside of you Mohawk Valley guys? I know this is the first time you've been here, but any new members or somebody's their first time here? Paula, this is your first time. But I saw you on the virtual star party, didn't I? Yeah, Paula joined us on the star party we had a couple weeks ago. Mike Malone, welcome, Mike. Can you tell us how you guys found out about us? Oh, Kevin Lyons is a longtime friend of Paula. So you've seen some of Kevin does a lot of planetary and lunar work. And so you've probably seen a lot of his images. He does a nice job.
Kevin and I actually go back to when we were 16 years old, and we were in the junior section of the RAS and used to meet first Friday every month at the planetarium. So we go way back. Wow,
that's fantastic. And Mike's been a member for a while, but first time he could attend a meeting. Well, these are always available. They're really easy. All you gotta do is turn on your computer. So welcome, Mike. Let's go to some observing. Anybody get some observing recently? I put a couple pictures up here of some solar observing that I know that people did. Bob, who joined you at the site when you guys took that image of the that sunspot group?
Well, Roger was at the site, Roger McDonough, and then Doug Kostic. So he and I spent quite a bit of time We wanted to do some imaging in hydrogen alpha, but the clouds were coming in, the sun was getting low, and so we stopped. I wanted to get out maybe yesterday, but couldn't do it to see that group before it rotates out of view, but just couldn't get to it.
I took a
It's nice to see the
moon recently.
I saw a couple images of yours, Mark, on of the moon that you took.
But it was mighty cold outside, so I didn't stick around very long.
Sam says he tried to look at Mars with his new eyepieces, but it wasn't dark enough and it wasn't in a dark enough place to see anything meaningful. And Mars is tough to look at through a telescope. That's even being fairly close. Dr. Richmond's all by himself. Eclipsing binaries, cool. Hooray. It can be a lonely chore, but some people like it that way. The image I have there is from our star party that we did a couple weeks ago. That was that's an image of Neptune and what I believe are 3 moons of Neptune. It was certainly 2, but possibly 3 moons of Neptune, which I found pretty exciting to see. I'd never seen the moons of Neptune before. That was fun to do. All right. So I want to remind everybody that it's membership renewal time. Your membership, unless you just signed up as a new member, if you sign up as a new member, you go right through 2021. If you sign up anytime after, I think it's July. But for our existing members, our memberships expire at the end of the month. And if you hold a key to the site, that also needs to be renewed. And you can use the form that's in the newsletter, or you can go to the website, go right to the website. There's the link there. It's just join-ASRAS. You can mail your check, or I know that our membership chair would prefer you use PayPal, and the fees are all in there as well to use PayPal. But if you need help doing it, Bill Rogers is available, and there's his email right there if you want to get a hold of Bill to renew your membership for the astronomy section and for the RAS. Any questions on membership renewal? We held a lot of people over into this year, but they will be expiring at the end of this year for anyone who has not renewed. All right, so virtual star parties, we had 5 so far. We're going to do 1 more before the end of the year. And if you want to see them, there's links on our website as well as in the newsletter. If you just go onto YouTube, if you type ASRAS twice, ASRAS space ASRAS, you'll get to our YouTube page, and the recordings of those sessions are there too. So the latest one was a planets a deeper look. That was about an hour long, and we'll do one. I want to do one on December 21st for the conjunction of Jupiter and Saturn. So plan on that night. I don't know if I could do that live, but I'll certainly pull it together that night, at least to do the observing, and then they'll schedule a date a little bit later to watch it if I can't do it live. So looking forward to doing that. And then if Bob has a nice sunny day, we might do a daytime star party with the solar scope. I was gonna join. I had to work the day that Bob and Doug went out there, but we'll catch a day when we can all get out there and do a daytime star party. That'll be kind of cool. All right, so coming up, the events for December, we're gonna have an open house on Sunday the 13th from 12 to 4. You want to visit the Ferris Center to see what's going on in the daylight. So guys like Mark can find out what's happening there at the daylight. Look at the buildings, look inside the buildings, get a tour. We'll be observing COVID protocols, which I'll describe in another upcoming slide. Sunday the 13th. Later that day, we will have a gathering for the Geminid meteor shower. Hopefully it's clear. Hopefully it's not too cold. we'll also be observing the COVID protocols there. The Geminid meteor shower has a projected zenithal hourly rate of 120, which is about 2 a minute. So that's at peak. That's at great conditions. You know, we need all that to be in effect to see that many, but that's a good 30% more than the Perseids were projected at for this year. So it should be pretty good. The Perseids were pretty spectacular if you were out to watch the Perseid showers. The peak is at 8 p.m. our time, and it's a shower that has a wide peak. So from 8 to 10 hours before and after that, you should be able to get a good rate of meteors. I look forward to that on Sunday night. So bring a lawn chair, bring your mask, and come out and have a good time. It should be if it's clear and it's fairly warm, it'll be a fun night. All right, so here's the protocols for the open house and the observing. We will keep a log in the Wolk building, the education building. As soon as you walk in that main door, on the table on the right will be a clipboard. Please sign in. So in the event that we need to trace contacts, we have your name and we can contact you with that. Hand sanitizer will be right there at the sign-in sheet. Please ensure there's 6 feet between you and other people. You need to wear masks if you're not going to be if you're going to be in that be talking and in 6 feet with around people. The building cannot have more than 30 people in it at one time. Any observatory building, the 2 big ones anyway, can't have more than 4 people in them at any one time. The bathrooms will be clean the day of the event, and they're available for use with these rules, and that you wipe the faucets and handles with the disinfecting wipes that are in there before and after use. Wipe the toilet seat if you use it or handle it before and after use, and then just dispose of everything in the trash can, because we don't have we're on a septic system, so we don't need to deal with all the paper with. So wash your hands, use a red light, and if you're going to be out after dark. And that's it. Enjoy the company. We can have a good time just using those rules. And yes, that Roger reminds me that the upstairs bathroom is closed for the winter, so we'll put the sign on that door. It'll just be the downstairs bathroom that'll be open. So thanks for the update, Roger. All right, and then we have a directors meeting this Wednesday from 7 to 9 p.m. Let me know if you'd like to attend. I'll send you a link to the meeting, but the board of directors will be meeting Wednesday, and I think in VAS it's the same night as your meetings, Joel. So we'll have to work something out if we're actually going to attend your meeting. So we'll talk about that at another time. But if any members want to attend our board meeting, you're welcome to do so. Just let us know. Let me know that you're interested in attending, and I'll send you a link to the meeting. One more thing we're doing is we're forming a telescope inquiry group, and I polled the membership to see who'd be interested in this. And I believe there's 5 or 6 of us that are going to meet on Tuesday next week and talk about how we address this. And because we get a lot of questions on how do I set up my scope? I think my scope is broken or missing parts, or can you help me? What scope should I buy for my daughter, my son, my husband, my wife? And it typically ends up going to it goes to somebody on the board or somebody very specifically at the website. And what I'd like to do is get a group of people together that we can address those questions to. So when we get this question, we can say, oh, this goes to the telescope inquiry group. And then these guys or gals can pick up the question and run with it from there. So we will be meeting on Tuesday, this coming Tuesday at 7:30. If you are interested in being part of this group, let me know, and I will get you involved in it. If you want help, we will give you instructions on how to contact this group to get the help that you want for your scope, or how to use your scope, how do you set it up, and what to buy. Sometimes that's the biggest question is, I want to buy a scope. What scope should I buy? And that's probably the hardest question to answer. It's a very personal question. What kind of scope should I buy? That is a blue button meeting, Tony. So if you're interested, I'd be glad to send you the link. All right, and then in January, our meeting in January is going to be Ranga Diaz, who is part of a group that did the first ever creation of a room temperature superconductor. He's also from the U of R, and this should be an interesting talk because superconductors have historically, and they're very useful for a lot of different reasons, but historically had to be kept at very, very cold temperatures in order to use superconductors. And the fact that they've been able to create a room temperature superconductor could be very interesting. And I think we'll have some questions on what the applications would be and what is the impact of being able to be at room temperature versus all the energy you got to put into being very, very cold. So that'll be our January meeting, and we will not be meeting on New Year's Day. We will be meeting on Friday the 8th, so a week late because that's a holiday. I think that's it. Any questions for me?
None for me.
I'm sorry, Mark.
I said nothing for me.
Okay. All right. With that, I will. I'm going to give Kelly Douglas control here. Where is she? So, Kelly, the control is yours. If you want to upload or share a screen, it's all yours. And you're on mute.
Yes. Let me.
There you are.
Hold on. Where's my. Give me just a second.
Okay.
I have my slideshow screen set up differently than normal for classes. All right. There we go. Okay. Fantastic. So, all right. So as Mark said, I'm Kelly Douglas. I'm a professor at the University of Rochester in the Physics and Astronomy department. And I wanted to share with you guys tonight a little bit of what I work on at the university and the upcoming DESI survey and what some of the science is that we can do with it. So DESI stands for the Dark Energy Spectroscopic Instrument. And so I'll talk a little bit about the telescope itself and the instrument. And I won't actually talk about the main science goals of DESI because that is not my my one hope with DESI. And so I'm going to talk a little bit about my connection with DESI and the research that I want to do with it. So I will say, if there are any questions while I'm going through this, please don't hesitate to ask, either in the chat. Well, I think in the chat while I'm talking, and Mark will interrupt me. I'm happy to take questions while I'm talking and sharing this with you. And I'm going to try to keep it as little technical as possible, but I do have to talk about some astrophysics. So if you're confused or anything, please stop me so that I can explain it in a little more detail. All right. So our universe, right? To understand how our universe formed, how our universe evolves with time, we need to be able to understand all of the individual components to it, because each one of those gives us a different piece of information that allows us to put together the picture of what has happened in our universe. How did it start? How has it evolved? And what is it going to do from this point on? That also allows us to understand where we are in the universe, and are we special? Are we not special? And what is our own galaxy like? So today I want to start with kind of these smaller individual objects in our universe, the galaxies themselves, talk a little bit about some of the details of galaxies, and then we'll move to the large scale structure of the universe and how we are going to probe that to regions that we've never gone before with DESI. So first, galaxies, right? What is a galaxy? That is a big question, and I know we all here, right? We love looking at them. We can take images of them with our telescopes and whatnot, but what really is a galaxy at the end of the day? Well, a galaxy is a collection of stars and gas that is all gravitationally bound together and is sitting inside what's known as a dark matter halo. All right, so what is that then? Well, if we actually look at the structure of a galaxy on a high level, we have the stuff that we can see that sits in the center. That's our stars and our gas. And that's what we take images of, right? Or we see through our telescope. That's what, for the galaxy, like as what's shown here, that's the pretty part that is awesome to look at. And when you think of a galaxy, you're thinking of the stars and gas. But this isn't actually the dominant component of a galaxy. Every single galaxy, no matter what type it is embedded within a spherical distribution of matter known as dark matter. And so we consider it a halo that sits around the galaxy. And dark matter is weird because we can't actually see it. It doesn't interact the way normal matter interacts. And so all we can do is infer its existence based on other observations that we make. So for example, dark matter makes up almost a quarter of the material, the stuff, the energy in our universe. But like I said, we can't see it with light. We don't see it. You can't, if you look in a telescope, you can't actually see dark matter. Instead, we infer its existence based on how it interacts with gravity on the stuff that we can see, on the luminous matter. So a really good example of this are galactic rotation curves. So if you measure how quickly a galaxy is rotating as a function of radius, you'll get what you see down here on the bottom. So these two little plots here, these are rotation curves. The x-axis is radius, starting at the center of the galaxy and moving your way outwards. The y-axis is velocity. What we would expect, based on just the material that we can see, is what's shown here on the left. We expect there to be a very sharp increase in the speed at low radii. And then once you get past the central region, this bulge, we expect the velocity to decrease with radius. However, when we actually make these measurements, what we see is what's shown here on the right. We see the velocity increase very quickly with radius, as we expect. But then as we move outwards to larger radii, the velocity doesn't change. It stays uniform. It's what we call a flat rotation curve. The difference between the rotation curve that we observe and the rotation curve that we expect based on the material that we can see is due to dark matter. So this is an example of how we, quote unquote, see dark matter, even though we can't actually see it. And unfortunately, that's about the extent of dark matter that we know. We know it interacts gravitationally. We can measure how much of it is in a galaxy or in a cluster of galaxies. But beyond that, we don't know much else other than that. We don't know what it's made of. We don't really know anything else about it. So that's kind of why it gets the name, right? It's dark because it doesn't interact with light, and it's matter because it does interact with gravity. All right, so my research is, I'm an extragalactic astronomer, more or less observational. And so what I am interested in are the properties of galaxies themselves. So we typically separate galaxies into two kind of major groups. We have spiral galaxies and we have elliptical galaxies. And each one of these has different properties, and each one of these, therefore, is at, we think, different stages in the evolution of a galaxy. Spiral galaxies are the ones that are really awesome to take images of. They're blue, typically, especially their spiral arms. This color is the result of very hot, very young stars that are currently living in the galaxy. These hot young stars, because they're so hot, they shine in the blue, and they're very short-lived. This is why the color of these galaxies tells us that they are currently forming stars. So spiral galaxies typically have a lot of gas in them, and that gas is what fuels the star formation. This is in sharp contrast to elliptical galaxies. Elliptical galaxies are much redder in color. They contain, their stellar population is only the old stars that are left behind. These are very small stars. They're very cold, typically. Not as cold, well, yeah, they're very cold. And so therefore they have a very red color associated with them. And because there are no hot stars anymore, there's blue stars, because there has not been any star formation in these elliptical galaxies in a very long time. The galaxies themselves just have this overall very red appearance. These galaxies also are typically much older as a result, because they only have those old stars. They're basically the combination of eons of mergers of the younger spiral galaxies that have merged together over time, and we think are the progenitors for the elliptical galaxies today. All right, so how do we actually learn about galaxies? What can we see? How do we study a galaxy itself to understand its properties? There's basically two methods. We can use photometry and we can use spectroscopy. Photometry is taking pictures. That's what most of us do with our telescopes all the time. So we image these galaxies, and that shows us the visual properties of the galaxies. We can figure out what its color is, whether it's red or blue. We can determine the galaxy's morphology. Is it a spiral galaxy or an elliptical? How many spiral arms does it have if it's a spiral galaxy? If it's an elliptical, how elliptical is the galaxy? Things like that. You get a very overall wonderful understanding of what the galaxy looks like. And some of these properties are only accessible by taking images. However, there's some information that you can't get from photometry, and that we use spectroscopy for. So spectroscopy, we take the light from the galaxies and we put it into a spectrograph, or a prism essentially. And we split that light up into its constituent wavelength ranges. That information gives us a different subset than what the photometry does. We can back out of the spectrum of a galaxy its relative velocity with respect to us, or its redshift. We can determine what its stellar population is. We can figure out what its gas composition is. Is it very metal rich? Or is it very young and immature and has just mostly pure hydrogen associated with it? Does it have a lot of neutral hydrogen? Does it have a lot of gas available to form new stars? Or does it not? Has it run out of all of that gas and can no longer form new stars? My areas of research are very heavily dependent on the spectroscopy, mainly for that relative velocity component, that redshift. So what is going into the spectrum of a galaxy? When we look at, for example, this image that's shown here on the right, what are we actually looking at here, right? I said, okay, it's the galaxy's light, it's split up, but we can actually understand a lot of the properties of the galaxy by looking at these various features in the spectrum. The easiest way to explain how the light works is by looking at the different components, because the spectrum itself is basically just the sum of all these different sources of light coming from the galaxy. Remember, a galaxy is a mix of stars and gas. If you just take the light from a star and you pass it through a spectrograph or a prism, what you end up with is almost a perfect rainbow. You get a continuous spectrum of light. There are no gaps in it. There are no breaks in it. And this typically follows a law that we call a black body spectrum. We don't care about that right now. If the star's light passes through a cloud of gas before it enters our spectrograph, then what we see is what's known as an absorption spectrum. The gas has absorbed some of the light that was originally coming from the star. And so what we end up seeing is more or less the continuous spectrum, but with some gaps in it. If we look at the cloud of gas off the line of sight of the black body, the star, so that we're basically just looking at the light coming from the gas cloud itself, then what we see is an emission line spectrum. We just see what material or what light the gas cloud is emitting. This light that is emitted by the gas cloud is exactly the same light that was absorbed by the cloud from the black body, from the star. So if you took an emission line spectrum and an absorption line spectrum and you added it together, you would get back a continuous spectrum. What we see when we look at galaxies is the continuous spectrum at the bottom of the spectrum from all of the background stars. And then we typically, if there's a lot of gas in the galaxy, we'll see an emission line spectrum on top or superimposed on the continuous spectrum. If it's an elliptical galaxy, we will see just an absorption spectrum on top of that continuous one. So if we go back for a second and look at my sample that I showed you here, this is an example of an emission line galaxy or an emission spectrum. We have the continuous spectrum from the stars down here at the bottom. And then superimposed on top of that, we have our spikes. Those are the different features from the gas that is also present inside this galaxy. All right. Now, the light, specifically those emission or absorption features, is really, really important because that allows us to measure how quickly the object is moving relative to ourselves. This is based on the simple Doppler effect, the concept that we're all familiar with when we hear, for example, a siren pass by us. The pitch of the sound waves from a siren as it passes by our face changes whether the source is moving towards us or moving away from us. If the fire truck or the ambulance is moving towards us, the wavelength is compressed. The sound waves are compressed, and so the pitch ends up getting higher. It's a shorter wavelength. When it's moving away from us, the wave gets stretched out, it gets longer, the pitch gets lower. Every single wave that is produced in nature, and this includes light because light is also a wave, exhibits a Doppler effect or can be subject to the Doppler effect. So if you have a source that's moving towards you and is emitting light, then the light is going to appear more blue than if it was stationary with respect to you. Conversely, if you have a light source and it's moving away from you, the light will appear more red. When we look at galaxies, let me go back a second. We can use these features to measure how much or how quickly the galaxy is moving and in what direction, if it's moving towards us or moving away from us. So how exactly do we do that, right? Because when we look at this spectrum, all we see are a pattern of lines. We don't see, how do we know which line is which? How do we know that it's not at rest with respect to us, that that's not where the lines are supposed to be? Well, thanks to quantum mechanics, it turns out that every single element in nature has a unique pattern of its own lines. It has basically a fingerprint. What I'm showing you here is the fingerprint for hydrogen. If you've ever seen illuminated hydrogen gas through a spectrum of some sort, through a prism, it's not a continuous light source like a light bulb would be, an incandescent bulb, I should say. Instead, what you see is a couple of very distinct lines. You'll see one in the red. You'll see one kind of on the bluish side of green, but pretty close to green. You'll see one definitively in the blue, and you'll see one down towards the violet. And it turns out that each one of these lines is actually produced by the electron that's living inside that atom. Every electron has very unique energy levels that it can sit in the atom. You can kind of think about it as levels in a house, except how many steps you have from one floor to the next changes. And every single house or every single element is different. And if an electron wants to move from one level of the house to another, it has to exert energy, right? It has to move downstairs, go down the stairs, or go upstairs. When you go downstairs, it's a lot easier. So you're actually giving off energy. And the exact difference in energy between one floor and the next is the amount of light, is equal to the energy of light that we see. So for example, if the electron moves from the third floor down to the second floor, it will emit an amount of energy that's equal to this wavelength right here. And if you're going from the fourth floor down to the second floor, you're going to emit more energy. So your wavelength is shorter and continuing on from there. As it turns out, every single atom, well, I shouldn't say atom, every single element has its own unique floor separation. And so this pattern, this specific pattern of lines that we see will only ever happen if there's hydrogen there. And therefore, whenever we see this pattern of lines, we know that that's hydrogen. We can compare where we expect these lines to be from where they actually are when we observe the object. And the difference between those two is due purely to the motion of the object with respect to ourselves, that Doppler shift. And this is what's known as the redshift of a galaxy. So once you identify the pattern of the lines in the spectrum, you can figure out how quickly it's moving with respect to us. So for example, this center spectrum here is as if the object were at rest with respect to us. So it's not moving. If the object's moving away from us, its spectrum will look like something like what you see on the top here. All of the lines are shifted to longer wavelengths, to more red light than when it was at rest. Conversely, if the object's moving towards us, it will all be blue shifted. Every single one of those emission lines, or absorption lines in this case, are shifted towards bluer wavelengths or shorter wavelengths. And by measuring how shifted the lines are, we can then measure how quickly that galaxy is moving with respect to us. Edwin Hubble was the first one to do this measurement, and he found that every single galaxy, excepting the ones closest to us, Andromeda and the like, are moving away from us. Every single galaxy in the universe is moving away. And Hubble, in addition to measuring the redshift of the galaxies, or their velocity, the y-axis here, he also measured the distance to them. And he used variable stars, Cepheid variables, to measure the distance to these galaxies. And that's how he got the value that was placed on the x-axis. And what he found is that objects that are moving faster with respect to us happen to also be living further from us. And so the further away you get, the faster that object is moving. And this, therefore, told us that our universe is expanding. The other option is that we are at the center of the universe and it's all moving away from us, kind of like an explosion. However, we like to think that we are not special or unique in the universe. And if we are not special or unique, and everything is moving away from us, that means if you put yourself on any other galaxy anywhere, they would also measure that everything is moving away from them. So it turns out that the entire universe is just expanding. All right. Yeah, I basically already explained this. So the light, as it's moving from a galaxy to us, when it's emitted from the galaxy, it's emitted at a particular wavelength. But as it travels to us, the space between ourselves and the galaxy expands, it grows. And as it grows, the light gets stretched with it. And so by the time the light actually reaches us, it's much more redshifted than what it was when it started. All right, I'm gonna stop here for a second. Have I put anyone to sleep, or are we all good so far?
I think we're good so far.
Awesome. Cool. All right, so because the velocity of these objects is related to the distance, if we measure the redshift to all of these objects, then we can figure out where they live in the universe. And so we know the RA and DEC of all of the objects when we target them in the sky. So by combining the sky coordinates of a galaxy with its redshift, we then can determine what its three-dimensional distance is from us, or its three-dimensional location in the universe, and we can make a map of that resulting distribution. So before I go into that and show you what the results are, I want to first kind of work our way outwards from our own galaxy, right? So we live in the Milky Way, of course. In this diagram, the Milky Way is at the center. We are part of a group of galaxies. So galaxies are typically clustered together into these groups. Groups consist of one or two, maybe three large galaxies. So in our group, that would be ourselves and Andromeda. And then surrounding each one of ourselves, we have a bunch of satellite galaxies. These are small galaxies. The Magellanic Clouds are an example of these satellite galaxies. And so around the Milky Way, for example, I think our count is up to about 30 or 40 dwarf galaxies. And in total in the local group, there might be about 100 of these dwarf galaxies, and then the 2 large ones. If we zoom out even further, you'll see that galaxies are clustered together. Clusters, galaxy clusters, are the densest regions in the universe. There are hundreds of massive galaxies that live inside galaxy clusters. So in this diagram, again, the local group is right here at the center. And you can see all these various clusters. The Fornax cluster is over here. We have the Hydra cluster down here. This entire thing is what's known as a supercluster. So if you have a bunch of clusters that are stuck together, you form a supercluster. But if you notice, there's a lot of space in between these clusters. The galaxies are not uniformly distributed in space. And it turns out, even when we go further than our own local group, which would just be in the very bottom part of this diagram here, galaxies are not distributed uniformly. Instead, they're clustered together into these clusters, and they're strung together between the clusters along filaments. And these surround very underdense regions of space, which we call voids. So these voids are what I like to study, where there's almost nothing, because they give us a lot of information about how a galaxy evolves. Galaxies that live in voids tend to be a lot smaller, a lot more isolated, and they really have not interacted with other galaxies. As a result, these void galaxies are as close as we can get to building our own galaxy, sticking it in a lab, and letting it grow. That's essentially what a void galaxy is. So my research involves building these giant maps of the galaxies and then finding these underdense regions. In this diagram here, the underdense regions, the major parts of them are highlighted by these blue circles. So you can see where all the empty regions are. You can kind of imagine it as soap bubbles. So you have a bunch of suds that are collected together. The soap material on the edge of the bubble, that's where the galaxies live. And the insides of the bubbles, now bubbles are typically empty, so you won't have any soap material in there, but imagine you might have a couple small bubbles inside. That would be an example of what the three-dimensional distribution of galaxies looks like in our universe. You can also think about it as Swiss cheese. If you're hungry or not hungry, maybe it's not good to think about Swiss cheese at the moment. You can also think about it as a sponge, or even as a kind of three-dimensional spider web of sorts. Whichever analogy works for you, that is the distribution of the galaxies in our universe. And we can use this distribution to understand how the universe evolved, because it shouldn't have started with all of these gaps. The universe should have started in the easiest state possible, a uniform distribution of material. So how did we get from a uniform distribution to this very wholly chunky distribution of objects? By understanding that evolution, we can understand how, what makes up our universe and how our universe evolves. So, okay, good. This video is decent, kind of. So this is a 3D rendering of what the voids look like. It kind of looks like a big brain. All of the little tiny red dots are galaxies. And you can fly through this distribution, and you can see that right now we're inside the voids. There are some galaxies that live inside them. And so you can kind of go through this, and you can explore what the three-dimensional distribution of objects in our universe looks like. All right, so how did we actually get this? Like I said, we think that the universe should have started out roughly uniform in its distribution of stuff. Turns out we think that there were very, very minor fluctuations in that initial distribution. And over time, as the universe expanded and gravity pulled together different components of it, those small, tiny perturbations in that initial distribution got amplified. And so regions that were just slightly more dense than average became even more dense. So you can see here in the center, there is some slightly thicker material. And as the universe evolved, that ended up becoming a very thick cluster of galaxies. Areas where there were very slight underdensities became even more underdense as the universe evolved with time. So what does that mean for the universe? We're pretty sure the universe started with a giant explosion known as the Big Bang and has been expanding ever since then. Great, so what's our future look like? Well, there's various models. They all predict the same thing now. That's a property of a good model, right? Is that it matches what we see today. Each one of these models starts with a Big Bang. But if you notice, each one of them has a slightly different shape to the universe between the Big Bang and now. And each one has a different future. Some collapse back down on themselves. Some just continue to expand, but at a uniform rate. And some accelerate in their expansion. And so if we look into the past and we try to measure the evolution of the size of our universe, that can tell us which one of these universe models is the one we live in, is the correct one, and therefore what's going to happen in the future. And this is the task, more or less, that DESI has set out to do. We want to probe the galaxy distribution further back in time than has ever been probed before, so that we can measure how this size changes, and therefore we can look to the future and know how is our universe going to evolve from here. So this again is a different kind of visualization of the image we were just looking at. What is important to notice, so the x-axis here is time. Future is to the right of the y-axis, and past is to the left. And you can see that each one of these different models has a different age associated with it. The age of the universe, or the start of the universe, when the Big Bang happened, is where each one of these curves intersects the x-axis. And so as the universe evolves, as it grows, what we want to do is try and measure which of these curves is correct. All right, so how do we do that? Well, one of the easiest ways to do that is to use what are known as standard candles. We can't just use the redshift of a galaxy, because it is, while the redshift is proportional to the distance, if things are moving faster than we expect or slower than we expect, if the universe is accelerating or decelerating, then that speed isn't uniform over time. And if it's not uniform, then it's not exactly a one-to-one correlation between the velocity and the distance. So we want to be able to measure the distance from a different metric. And one of the easiest ways to do this is with standard candles. The idea of a standard candle is that you know how bright the object is. And therefore, the only difference between how bright you expect it to be and how bright it actually is just a function of the distance. You take an object, a candle in this case, you move it further away, it's going to get fainter. And you know exactly how much fainter it's going to get based on its distance from us. Well, this is awesome, except we can't exactly just take a candle and set it out into the universe to measure a distance. And we sure as heck can't stick, see candles on other galaxies to be able to observe them. So we need to use objects in the universe that are the same and are always the same brightness, so that when we detect them somewhere else, we can fairly accurately measure their distance. One of the best objects for this is a type 1a supernova. So type 1a supernovae are explosions of a white dwarf star that has reached the maximum mass. So white dwarf stars can be no more than 1.4 times the mass of our own sun. If they surpass that mass, they collapse and then explode. And that explosion is a type 1a supernova. Type 1a supernova, therefore, are a standard candle because it's always the same amount of material that's exploding in exactly the same way. You take a star, or a white dwarf, you pack on enough material to make it equal to exactly 1.4 solar masses, and it goes boom. So it's a standard bomb, if you'd like to think about it that way. Now, the result of type 1a supernova are these lovely nebulae that are awesome to look at. And the nice thing in particular about type 1a supernova is that they are much, much brighter than most other objects in our universe. They're not the brightest, but when they go off, they can outshine a galaxy. So when we see a type 1a supernova, we can see them from very, very far distances. And therefore, we can map out the universe to much higher distances than normal. So a team of scientists did these measurements in the late 80s and early 90s. And they measured the redshift, or the velocity, of these supernova. And they measured the brightness of the supernova. And if redshift is exactly proportional to distance, and therefore the universe is just expanding at a normal rate, we would expect there to be a very linear relationship here. But what we end up finding, it's a little easier to see on this bottom plot, is that the points diverge from a boring universe, I'll say, one that's not doing anything except expanding at a constant rate. They diverge upwards. The supernova are fainter than we expect them to be. That tells us then that the universe is not only expanding, but it's expanding faster with time. So we are in an accelerating universe. That means that there's something pushing our universe to expand faster than if you just had an explosion at the beginning and you let the material coast from there. So something is acting almost like a spring and is pushing out and expanding space faster than what we expect. All right, what is that stuff? That's a great question, and we don't know. We call it dark energy. Turns out dark energy is like 70% of the universe. Remember, we talked about dark matter before. That's a quarter of the universe's energy. Dark energy is over 70%. The stuff we can see is less than 5% of the universe. What dark energy is besides just the thing that is causing the universe to accelerate in its expansion, we have no idea. And that's what DESI's goal is to do. Measure how the universe is expanding to try and understand better what the properties of dark energy are. All right. So what is DESI then? I've been talking about it. I've been hinting towards it. What actually is it? Well, as I mentioned, DESI is going to build the largest galaxy map to date. You saw the initial wedge plot that I showed a couple of slides ago that had all those blue circles on it and the red and black dots for the galaxies. The volume that was shown in that plot is just this little tiny wedge down here at the bottom. DESI is going to probe out to a redshift for galaxies of about 1.5. It's split up into different samples. We have the bright galaxies nearest to us. There's going to be about 10 million of those that we are going to measure the spectrum of. Next out are the luminous red galaxies. These are like those giant ellipticals that we talked about, but these are the super bright ones. So we can see them to much higher distances. And then the most significant chunk of DESI are the emission line galaxies. There's going to be about 17 million of these galaxies for which we will be measuring their redshifts and can therefore map where they live in the universe. And then finally, the most distant objects that DESI will be looking at are about 2.5 million quasars and their corresponding Lyman alpha forests. Quasars are galaxies with a supermassive black hole at their center that is actively accreting material. And it's spewing a buttload of light out. And they're super, super bright. And that's why we can see them out to a redshift of 3 or so. And so what we'll be measuring then for these Lyman alpha forests is the absorption of that light as it passes through the material in between galaxies, between the quasars and us. All right, so this is what DESI is measuring. How do we pick which galaxies we're looking at? We use what's known as the legacy survey. So this is a survey that was done in preparation for DESI. It's separate from DESI though. All the data is public. You can go to legacysurvey.org and you can explore the sky. This is a screenshot of what you'll see if you go to that website and click on the Explore. Every single one of these little circles, these tiny spots that you see on here, those are targets that DESI will be targeting and taking spectra of so that we can measure their redshift. These kind of fainter, larger blue circles that you see, these are properties of the DESI instrument itself. These are what we call the patrol radius of the fibers. And I'll talk about the fibers in a second. All right, so what is DESI actually? DESI is a spectrograph that is living on the Mayall telescope down at Kitt Peak National Observatory in Arizona. It's a 4-meter telescope. DESI itself is sitting up here at the top. This is the focal plane, and this has all of the spectrograph, or sorry, not the spectrograph, the fibers. I'll talk about those in a second. The light from these gets fed down into a control room where we have all of the spectrographs where the light is split up into. So what actually happens to the light when it comes in the telescope, right? We're bringing in the galaxy and starlight. It's coming in and reflecting off of that primary mirror, going up through a set of correctors, and then intersecting the focal plane where I'll say the the addition to the field that DESI is making is sitting. All right, so what is this thing? I keep alluding to it. DESI itself, the instrument, is a series of petals. So what you're seeing here are those, every single one of the fiber optic petals or fiber optic cables illuminated, backlit, so that you can see what it looks like if you were sitting on the primary mirror and looking up at the instrument. There are a total of 10 petals as part of DESI, and each petal has 500 fiber optic cables that are controlled by a tiny robot. So there's a total of 5,000 fiber optic cables on DESI. That means DESI can take simultaneous spectra of 5,000 objects at the same time. That is just mind-blowing. It's crazy. One of these cables, or fiber optic cables, looks and housing is shown up here. The actual fiber itself is sitting at the very end. You can see it if you squint really, really hard. You can see it. It's actually shown here. There's 2 motors. These 2 motors are what control the position of the fiber. In previous sky surveys, like the Sloan Digital Sky Survey, for example, how the fibers were placed on the sky was very human intensive. You basically took an image of the sky and you figured out where your targets were. And then you drilled the exact location of those targets into a giant aluminum plate. And every single day, somebody had to sit down and plug each one of the fiber optic cables into one of those holes. So at night, that plate could get put on the telescope and then collect the light coming from those galaxies. As you can imagine, it takes a long time, therefore, to switch orientations and switch targets. That's not the case with DESI. We can rearrange the position of these fibers, I think, from startup to cool down, because there is some heat generated when all these little motors are turning, is about 5 minutes. So in 5 minutes time, we can rearrange the target location of every single one of these fibers and get a new 5,000 targets. Now, every single one of these fibers is fed down to 3 spectrographs. And what you end up getting out at the end of the day is something that looks like this. For each one of those petals, you have a different fiber that's sat arrayed out here on the x-axis, and the wavelength is on the y-axis. So the light is getting spread from each fiber in the vertical direction. These horizontal lines that you see running through all the spectra, those are your sky lines. So they will be subtracted out. And unfortunately, as you can see, they are vastly dominating all of the features in the spectrum. So before we can do any sort of analysis, we have to do a lot of post-processing to get rid of all of those objects. The other kind of looks like scratches that you see on here, the scratches themselves are actually cosmic rays that are coming down. And so those also have to be removed from the data before you can actually use it for science.
Kelly, Jeff asks, how big of an angle can an individual fiber make relative to the petal it's in?
That's a great question. So each fiber, well, let's see if I get my numbers right. Each fiber is, I think, make sure I get this right. It's a, hold on, I might have it. It's like 1/10 of an arc second, or it's an arc second. I don't remember which. Is the actual diameter of the fiber itself. And then it can patrol a total radius of, I think it's 1.4 arc minutes. Yeah, that sounds right. So the entire field of view of the entire array. So this whole field of view is 8 squared degrees. Good question. And I should have had these facts written down. All right. So we actually had first light at the end of 2019. And so the first spectra we took was of the Triangulum galaxy, so M33. So this was the footprint as it was laid out on top of the sky. So you see M33 down here. So just on M33 alone, we probably had about, I would estimate 200 fibers or 150. So we had 150 spectra that we took of the Triangulum galaxy. So one of those spectra from one fiber is shown here. You can see it's split into 3 different colors. These are for the 3 different spectrographs. So we have a blue arm, we kind of have a green arm in the center, and then we have a red arm on the far side. If you care, the spectrograph of DESI is one of the highest resolution spectrographs that is on a bulk size that we're working with here. One of the big things that it was designed to be able to measure or to differentiate with is the O2 doublet that you can see right here. So you see 2 little peaks here in the spectrum. This corresponds to this galaxy out here. This is one of the emission line galaxies, one of those 17 million galaxies that we're going to measure. And this galaxy has a redshift of about 1.6. So this is one of the most distant galaxies that we've been able to observe using one of these massive sky surveys. So what do we do with all this information, right? We had our collection of stars and gas. Those galaxies, as we've seen, are distributed on a cosmic web-like structure. And it turns out that that structure is the result of amplified perturbations in the original distribution of matter in the universe. And so by studying the pattern of the cosmic web, by studying how it appears and how it's changed through time, we can then probe what the universe is composed of, and therefore we can better understand dark energy, for example, and the different components of our universe. All right, because this was a presentation related to DESI, I have to put up our DESI credit slide, but that is all I have for you tonight, and I welcome any questions.
Questions being typed in now rapidly as we speak, as we wait.
Awesome.
Just as it sounds likely you are mainly targeting known object, do they ever go fiber fishing?
That's a great question. Unfortunately, no. We do have to make sure that we put the fibers on an object that we know exists. Otherwise, I shouldn't say that. There will be some fibers that are just kind of pointed out into space. Typically, those are either used for calibration, so to just kind of get the normal, like the skylight to be able to help us calibrate our spectra. Or there wasn't a target within this radius that the fibers can actually point to. And so if there's nothing there to target, we can't close off any individual fiber, so it's still going to collect light. So no, unfortunately, there's not going to be much fiber fishing. That being said, if the fiber doesn't fall exactly on the target itself, then we could end up detecting something that we didn't expect. We've also just, so we had just started, so we finished commissioning the instrument in March, and we started taking the first data for our survey validation. And by the time so we only got like 2 nights of data in before we had to shut down the telescope because of the pandemic. But just in those nights, we were able, it's kind of been a blessing in disguise, because we've had the last 9 months to look at that data and to modify and improve our systems drastically. And one of the things that we discovered while looking at the spectra that we collected is that a lot of the time, well, not a lot, and a not super rare occurrence, a lot of times when we put the fiber down on a target, we actually end up picking up 2 targets in the fiber. And so we end up seeing 2 different objects that are overlapped from each other, and causes a lot of problems in our pipeline. But from the science perspective, it's awesome because you're getting 2 spectra for the price of 1.
Interesting. Bill asked, some of the fibers were dark. Are they bad sensors or just not online at the moment the image was taken? The weird one. This one. So there are a couple of breaks in the where the fibers are laid out on the CCD that's taking this, so that way we don't have we can avoid a little bit of bleeding between the different fibers. But when we did our first runs, there were a reasonable number of fibers that, for one reason or another, were not getting their light from the telescope down to the spectrograph. And so it kind of was either random or was like a giant chunk. So for example, the periodic dark ones that you see here, those are supposed to be there. This single dark one that's here, that's probably a fiber that was not working for whatever reason. Interesting. Nick asks, how long does it take to acquire a spectra?
Good question. That depends on the target. So remember, I specified all these different target classes. Each one of them has a different survey strategy. So the bright galaxies, for example, these 10 million, those are only 130-second exposures. We will do, I think, 3 passes over the course of the entire survey. So we'll get 3 spectra, each of them 130 seconds in exposure, and we'll co-add, we'll stack those to get a better signal to noise spectrum. The other objects, the emission lines and the luminous red galaxies, those I believe all have on the order of like 1,000 seconds of an exposure, and there's going to be 5 exposures, I think, for each of those. And that's because they're just much, much fainter objects. So you need more exposures and a higher signal to noise to be able to see those individual lines that we were talking about. DESI itself, though, is not it's a very high resolution spectrograph. That's what allows us to discern those doublet lines. But it's not a high signal to noise survey. Basically, the goal of DESI is to get a redshift for an object and then move on. And so, unlike the unlike the spectrum that you see here, where you notice the noise is very, very low, and you can see these emission lines really well. This is from the Sloan Digital Sky Survey. DESI will not be will not produce spectra that have this high of a signal to noise. It'll be a lot noisier, but the goal in DESI is just to see these strong lines to be able to get that, that redshift.
Tony asks, how long is the expected service life of DESI? And what's the timeline as far as anticipated data collection?
That's a good question. DESI is going to be, the initial stage of DESI is a 5-year survey. So we are going to be collecting 30 million spectra over the course of 5 years. Was originally supposed to start in 2020, but because of the pandemic, we're more or less about a year behind. We have started recommissioning the telescope. So we should be able to start, hopefully, taking the survey validation data, so kind of the pre-survey data, to make sure that everything is going to work the way we expect, in like late December, early January. And so right now, the survey is planned to run 2021 to 2026. And we're already starting to plan out what we're going to do with the spectrograph after 2026, so DESI 2. And so the spectrograph itself is cutting edge. This is the most advanced spectrographs that we have, and the most advanced fiber optic moving robotics that is currently in development. And so other surveys are kind of being designed based on our technology. And so we expect that the actual instrument itself will probably last for, we'll probably be taking data, I would expect, for at least 20 years.
Wow. Cool. Jeff asks that the cosmic ray streaks imply that they affect fibers that are close to each other. How is your graph laid out in relative to fiber geometry?
That's a good question, and I honestly don't know the answer. Get back to it. Ugh. Here we go. Yeah, so I'm not entirely positive what the geometry is. I would assume, so each one of those petals, right, is a giant triangle. So I would assume that the fibers are fed, let's say, from the inside to the outside, and that's how they're arranged on here. So they are roughly in order with respect to each other. But yeah, I don't know for certain what that orientation is.
Any other questions? I got somebody typing a question. Well, they're typing. Were there any surprises from the spectrograph that you got from the Triangulum Galaxy?
I don't think so. I think it was more of a proof of concept than anything else. Yeah. I mean, the Triangulum Galaxy has been studied a bunch, so I don't think there was anything unusual. This was also, I think, like the first night of data that we took. Wow. So I don't know how much that spectrum has actually been analyzed, more than just a, hey, look, it worked. We got the emission lines we expected.
Paula asks, who designed and constructed DESI?
Oh, so there's a number of people that have been responsible for DESI. The survey itself and the instrumentation is supported in large part by the Department of Energy. Hence the dark energy component. That's why we're looking for it. And a lot of the big players in the design and implementation of the survey are those that were heavily involved in the BOSS survey as part of the Sloan Digital Sky Survey. So Michael Levy, Daniel Eisenstein, David Schlegel, and other people in that cohort. But at this point, it is a collaboration that spans the entire globe, very heavily supported by people at, for example, the Berkeley Labs. And I think a lot of the construction was done at Ohio State under Paul Martini's guidance. And then also a significant amount was done in, I think in France. A lot of the fibers were produced over there.
And Bill asked if there's any Rochester locally sourced content in the instrument.
I don't think there is. We have Rochester, well, the University of Rochester kind of came into the game a little late, about when I started at the university, so 4 years ago now. And our involvement on the instrumentation side was mostly with kind of post-processing and dithering of the fibers and the telescope to understand better the positioning and where everything needs to be located, besides the science aspects of what we want to do with the data afterwards.
Right. Jeff asked, what's the farthest known galaxy that's moving towards us?
The only galaxies that are moving towards us are part of the local group. Everything else is moving away. So that would be, the biggest one would be Andromeda. I'm sure there's a couple of satellite galaxies around Andromeda that are technically moving towards us as well. So yeah, it's just the local group where you'll find motion towards us. Otherwise, everything else is moving away.
So, well, I'm certain there's got to be some calibration to do this, but would it be possible to measure galaxies that are moving towards each other outside of our local group?
Oh, and therein is the big question. So you're absolutely, you picked out the biggest issue with building these maps, right? Because the velocity that we measure from the redshift is both the expansion of the universe and the peculiar motion of the galaxies, so how they're moving with respect to each other. And so we do end up with a distortion along the line of sight for the galaxies. So let me see if I can go back to my sky map. Here we go. So if you notice in this plot, there are features where it looks like a large cluster is kind of strung out along the line of sight. And just in general, if you notice, there's a lot of linear features that are kind of pointed as if they're pointing to us. That's what's known as the finger of God effect. And the idea is that these objects aren't actually strung out on this line. They're in a spherical, roughly spherical distribution. But because of their relative motion to each other, we can't disentangle that relative motion from the expansion. And so we kind of get both of those redshifts together. And what we end up measuring is stuff that in the cluster happens to be moving towards us. When you combine that with the cosmological redshift, the object ends up appearing a lot closer to us than what we expect. And on the opposite side, stuff that just happens to be moving away from us in the cluster. When you combine that with the cosmological motion, it appears to be much further. And so roughly spherical distributions end up pointed kind of along the line of sight. Because there is that preferential direction, because things tend to be strung just along the line of sight due to this, this peculiar motion, we can use that to try and back out what the actual position of the galaxies are. And so a lot of times we'll use this and we'll kind of approximate what the matter distribution is of the galaxies and try to move them backwards in a sense. And then from that, we can disentangle what the peculiar velocity is of the galaxy versus its proper motion.
Wow. Interesting. So all we really see is an apparent location, not really where it's at.
Exactly. And that's what is so important with looking at using distance measurements. Well, I missed it. Using distance measurements like the standard candles, because that gives us a separate distance. And then we can compare that distance to the redshift, and that gives us the peculiar motion as well. Because, for example, the luminosity of the object, right? That's not really going to change if it happens to be moving just a little bit away from us or a little towards us, because that distance, it won't be that different. And so we use standard candles. There's another thing called standard rulers that you can use. So if the object, you know how big it is, then you can measure its distance from that method as well. And you compare the redshift distance to that, and you can infer what the proper motion is. You can also use how quickly the galaxies are rotating, because it turns out, for example, spiral galaxies, their rotation rate is proportional to their luminosity or their brightness. And so if you can measure how quickly they're spinning, that tells you how bright they actually are, and you compare that to how bright it appears to be, and that gives you the distance. So that's similar to the type 1a supernova method.
Right. Jeff asked, I don't know if this is facetious or not, standard candle quasars?
So basically our quasar standard candles.
Yeah.
They unfortunately are not. We actually we don't understand the mechanism that's inside inside a quasar well enough to be able to predict how bright it should be. Quasar luminosity is highly variable. So if you make the light curve of a quasar, it's basically random noise. And so it's really difficult, therefore, to predict exactly how bright they should be, to then use them as standard candles. So yeah, quasars are the brightest thing in the universe, so we can see them out really, really far, but we can't use them as a distance measure, unfortunately.
Right.
Other than, their normal redshift.
Okay, so one more person typing here. A couple people typing.
It's all this pressure to type out your question.
Right. So David Bishop asks, will a type 1a supernova will show up?
In DESI? Yeah, so quite possibly. We're actually, part of the group at the University of Rochester is building a machine learning algorithm to detect, basically take in the spectrum and pick out which ones have type 1a supernova in them and which ones do not. They're not super common. Type 1a supernova, like I said, are the result of a white dwarf that happened to accrete enough material that it blew up. So you kind of need a lot of special circumstances to get to that point. Our galaxy, we're actually overdue. So I think we expect like one supernova per century. And we haven't had one for a long time. So we are overdue for one. And so astronomers are like eyes to the sky waiting for something to explode. But yeah, in general, we do expect to find just, serendipitously be taking the spectrum of a galaxy when it happens to be have a supernova inside it. And so that supernova, because they typically they can get pretty close to the brightness of the galaxy, it will dominate the spectrum. And so yeah, we're setting up pipelines to be able to find those and then do follow-up observations of those supernova afterwards.
I think Paul wants a clarification. Dark energy and dark matter take up so much of the universe, and you don't know what they are made of. How do you tell the difference?
That is a fantastic question. They do inherently do different things. So dark matter is that it's matter, it's material. So it interacts with gravity, and it acts exactly the same as regular matter, regular material. So if you have, a lot of it, it's going to have a larger gravitational force than if you have just a little of it. Dark energy, on the other hand, is, like I said, we don't know much about it. It is the theoretical explanation for why the universe is expanding at an accelerating rate. So basically, we need something to be anti-gravity. We need something to push out on the universe to make it expand faster than what it would if you just had material that blew up in the Big Bang and continued to expand after that, so unconstrained. And so they do different things, right? So dark energy is responsible, you can kind of think about it as a pressure. It's pushing out against the universe and causing it to expand. Whereas dark matter is just like normal matter. So, you know, what we're made of, it just doesn't interact with light. It doesn't give off light. And so we can't actually see it.
Thanks. A couple more people typing questions here. Tony asks, are there other data streams from other instruments that you anticipate will be helpful to DESI?
That's a good question. So at this point, the big predecessor to DESI that really helped us out was the completion of these legacy surveys. So there's actually a couple of different surveys that were done from which we got the imaging from. And so one of those, so there's a couple of them, like I said, and so that's kind of the main source for the extra addition to DESI. So DESI is just a spectrograph. It's not, it doesn't have a traditional camera on it like you would expect to take pretty pictures and whatnot. One of the upcoming surveys that will complement DESI is LSST, so the Large Synoptic Sky Telescope. I think I got that right. So LSST is basically going to make a movie of the sky. So that is just a photometric survey. They're just going to point their telescope at the sky and let the sky pass overhead. And they're going to do that, I think, over the course of 10 years. And so they'll have a 10-year movie of what the sky looks like, because they'll be able to observe the entire portion of the sky they can see in like a week or a month, something like that. And so that will complement DESI, because we will have all these redshifts for these objects, and LSST will then be able to see all these objects really well. They'll have really nice photometry. And so they'll be able to take their objects and they can find the redshift for that object from DESI. Another really useful kind of complement that DESI will help with are gravitational wave detections. So right now, when a gravitational wave is detected coming from somewhere in the sky, it's typically localized down to about a 10-degree patch on the sky. And DESI's focal plane is 8 square degrees, right? So as kind of a legacy redshift catalog, when these gravitational waves are detected, they can go to the DESI data and find all the objects that are potentially the source of that gravitational wave. They can get the redshift from DESI. At the moment, we don't have any of that. So right now, when there's a gravitational wave detection, there's a buttload of follow-up observations that are done to try and take redshifts of all the possible candidates to figure out which galaxy was actually the source of the gravitational wave.
Jeff asks, what's the expected level of certainty expected for the expansion rate as measured by DESI?
We will be measuring the Hubble constant, which is the expansion rate, down to, I think it's a factor of 10 better than any of the current measurements. Really, we will be measuring the kind of the relative components of the specifically how curved the universe is. So that's how we measure how dark energy has affected the expansion of the universe. We want to try and measure. Let me see if I can go to this plot. Yeah, so these different snapshots in the past, kind of cross sections of the universe, they all have different sizes associated with them at the same kind of time in the past. And so what we are really doing to measure the expansion rate and therefore dark energy is we're going to measure the size, the characteristic scale of the universe at these different components. And we will be measuring that at the limit of cosmic variance. So basically, even if you were to get more data, we wouldn't be able to do a better measurement of it.
Mike asks if dark energy or dark matter have relevant effects within galaxies or solar systems, or just solely external.
Yeah, so dark matter is not going to affect us on a solar system scale. It turns out that the amount of dark matter increases with distance from the center of the galaxy. So the further out you go, the more dark matter you'll find. And that's what helps to kind of counterbalance the galaxy itself. So the further out in the luminous matter, right, the further out you go in the galaxy, the less stuff you find. And so in order to keep that velocity constant, you need to have an increasing amount of material. And so you tend to have a lot more dark matter on the outside than you do on the inside. So it actually means that within the galaxy itself, there's not that much dark matter floating around in between the stars and the spiral arms. It's mainly contained in that dark matter halo. And so it kind of serves as like a buffer on the galaxy. So dark matter definitely affects the rotation of the galaxy, and it affects how the galaxy evolves. Because the dark matter, we believe, is what formed first. So dark matter is much more dominant in the universe, right? 24% of the universe is made up of it versus only 4% or so of regular material. And so really what we think happened is that it was the dark matter distribution that resulted in the location of all the galaxies that have formed today. And so that dark matter is what collapsed first into these halos. And then the rest of the material, the normal matter, what's made, what stars and gas are made out of, that kind of followed along and fell into the dark matter halos and then formed the galaxy on the inside. So the dark matter has a very significant influence on how a galaxy forms and how it evolves. But for the individual components in the galaxy, like solar systems, individual stars, even binary systems, it really doesn't do that much.
Very good. Well, Kelly, thank you so much. We appreciate your coming to visit us.
Absolutely. Thank you for having us.
Share with us, if you will, what courses you're teaching next semester, and if we're able to audit those, that would be phenomenal.
Yeah, absolutely. So I am teaching 2 classes next semester. One is the Intro to Astrophysics. This is typically what our sophomore level students take that are physics and astronomy majors. So that you're more than welcome to audit that. It will, for those of you who are auditing 111 right now, it will move at a much faster pace, and it has a lot more math. But that being said, there are a lot of really pretty pictures, because we talk about the formation and evolution of stars, then we talk about galaxies, and that's where all the pretty pictures are. And then we do a little bit of cosmology at the end. The other class that I will be teaching is the Advanced Observing class. So I think a couple of you audited that last spring with Professor Watson. So you're welcome to audit that again, or if you didn't get a chance to do it in the spring, you can do it with us this spring. So that class basically consists of remote observing because of COVID from using the Mies Observatory down just outside of Bristol Springs, and of kind of whatever experiments you want to do. So if you audited audited that class, you would probably be joining up with the students and kind of participating as part of their observations, just because the weather's not great up here. So we don't have a fantastic number of nights for everyone to observe.
That's true. That's true. Cool. All right. Well, thank you so very much. Appreciate it.
Yes,
Thanks,
thank
Kelly.
you.
I would encourage, if anybody else wants to chat for a bit, you're welcome to turn on your camera, say hello, say goodnight, whatever. Glad to have anybody come on. But thanks again so much. We're not going to run over to Applebee's and have wings and a beer tonight. So.
Darn.
Yeah, right. That's what we usually look forward to after one of our meetings. We'll typically meet this time of year. Actually, this meeting would have happened at the planetarium, but we can't have this many people there.
Yeah, that would have been awesome.
As an aside, for those of you that are still here, I've been you know that I work at the planetarium on a part-time basis, and I've been able to work a couple of shifts here and there. And in my spare time, I have figured out how to do full dome images for members on the dome. So when we can meet again, we can spice up our member images show up on the dome of the planetarium. So more to come on that the next time we're able to meet there. You have lots of compliments tonight, Kelly. Thank you so much.
I see that. Thank you. You guys were a good audience. I enjoyed this.
Good. We enjoyed the talk. Nobody's talking except you and me.
I know.
I got lots of chat. Got lots of chat.
There you go.
Thank you. Very interesting, fascinating talk. Nice model, NGC 17. Oh, never mind. That's a Star Trek reference.
Thank you very much. Yes. This was a wedding gift for my husband and I a year ago. Yeah.
Now I see. I had to blow up your picture. There it is. Very good.
It's also a little dark in here now.
Yeah.
I also have the Saturn. So my husband is obsessed with Legos. So these are all Lego models of, the Enterprise. And we also have the Saturn V up here as well, which I think you can just kind of barely see.
Oh, laying on the side. Yes.
Yeah.
Yes. You're good. Yeah. Very good. Bill's very good at noticing stuff like that.
I like having it in the back in my view, because especially for my students when I'm lecturing, they need a little bit of distraction, to kind of look in the background and be like, oh, what she got behind her.
There you go. Very good. Very good. That's it. Well, thanks. Thank you very much, Kelly. Appreciate it. Thanks for coming on board. And thank you everybody for coming tonight. I thought we really enjoyed that. So till next time.
All
thanks.
Right.
You guys enjoy your holidays.
Yeah.
And I'll see you guys in January. If I don't see you at the site for the Geminid meteor shower or for the open house. Thanks for coming, everyone. Have a good night.